Hi everyone, thanks a lot for the love and support on my single cycle processor design video. I'm really happy you liked it. Now it's time to move ahead with something even more exciting. Here is the flow of our pipeline processor design video series. Yes, pipeline processor design. In pipeline processor design, first we add the pipeline registers, then we deal with hazards and much more. Here is the quick overview. In this series, we will take our single cycle RISC-V design and turn it into a pipeline processor. Pipelining helps us run multiple instructions at the same time, like an assembly line, to make our processor faster and more efficient. We will start by adding the pipeline registers like instruction, fetch, instruction, decode, a register here, instruction, decode and execute and memory access and write back register. These registers separate each stage and help us move instructions smoothly from one state to the next state. Here you can see the all the pipeline registers with control unit. When we add pipeline registers, new problem show up. These are called hazards. And there may be data hazards, control hazards, or sometimes structural hazards. To fix the data hazards, we use something called forwarding or bypassing. It helps by sending the data directly from one stage to other instead of waiting to write and read again. This keeps the pipeline running without delays. Now we will update our processor with pipeline register, forwarding logic, hazard detection unit. These make our processor smarter and ready to deal with most hazard during execution. For control hazards, we will use two methods. Flashing actually clear the wrong instruction after a branch. Here you can see we introduce the flashing signal here in the instruction fetch and decode register, first pipeline register. Um, then branch prediction actually guesses the path early to save the time. Both help us avoid wasting cycles and keep the pipelining flow. So far, we have built a full pipeline processor with pipeline stages, hazard handling, forwarding, branch control. It's now working pipeline RISC-V data path. At the end, we will also talk about exception, things like illegal instruction or memory misaligned access. We will also see how a RISC-V pipeline processor detect and handle the exceptions safely without crashing the system, how it deal with interrupts. We will also see. Thanks for watching. If you like the video, hit the like button and subscribe the channel. Join me on this exciting journey. Let's learn and design. Here I'm using Vivado 2019.1 for writing Verilog code and simulation. Here is a previously designed single cycle Verilog code. Let's copy it. Copy this code before test bench and paste it here. So here is the same single cycle RISC-V Verilog code which we previously now let's modify the single cycle design for a pipeline. Before the first pipeline register instruction fetch and instruction decode, the module here we have mux program counter, instruction memory, and adder PC plus 4. So first here we have a program counter, PC adder, here is a mux and instruction memory. Then after instruction memory here we need to add the pipeline. Register first instruction fetch, instruction decode page, let's see, and instruction fetch, instruction decode. I name it instruction fetch code register. Audio. Okay. Um, After instruction memory here we have the first pipeline register, instruction memory, and instruction fetch and instruction decode register. The first signal here we have a clock reset. Here the one input here you can see which is directly from the output of this program counter, and the one input for this IFID register which is actually the output of this instruction memory. So for the input instruction fetch program counter in, and the input instruction fetch I name for program memory instead of instruction memory. um, now same for the output instruction decode PC out and instruction decode program memory. Here clock and reset are the single bit input, and instruction fetch PC in, and instruction program in are the input, and both are 30. Also 32-bit wide. Instruction decode program counter out. Instruction program memory out. Clear both of them. Okay. Now here you the always procedural block edge of sorry, out of procedural block, and here is the end of procedural block. When the reset signal is high, then both the output signal instruction decode program counter uh, out out at 0. Similarly, instruction decode program memory 32-bit. Okay. Else begin instruction the same value at and fetch PC in program memory here we need to here is the end of always procedural block, and this module. So here is a just we add the instruction fetch, instruction decode, pipeline register. Um, no, let's make the instance of this register in the top module. There is our top module. After program counter, PC added, PC must instruction memory. After instruction memory, here we add this ID. Is a instance name. I use the same instance name, instruction fetch, instruction decode, register, clock with clock, and reset with reset signal. Here is the input from program counter. Here is the input from instruction memory of program counter. After this pipeline register and the output of instruction memory is pipeline. So the input of this uh, program counter is actually the output of this program counter, which is connected the input by using this wire. So pick this wire and program memory, actually the output of this instruction memory. Here I use a decode wire. Decode wire is connected with. So here we add the IFID pipeline register just after instruction memory. We add the test bench. So here you can see the pipeline register. First register instruction fetch and decode. Here is the output of this register, the same which is at the output. Here is a 4 of program counter input. Here you can see 4, 8, 8, 12, 12, 16, 16. Here is the instruction at that address, at the address of 8 we have this instruction, and here you can see at the address of 8 we have this instruction, the same instruction which is the input. uh, we have the same instruction at the output. So here you can see the instruction at the address of 12, here the same instruction at the address of 12, and similarly